This is the second application of neural net control that I'm going to show you, combined with the active flow control lecture that is in a separate video. This one is about a bioreactor, and it's a system that makes a good application for neural network control because it's highly nonlinear. There's delayed feedback and time lag, which makes it hard to control. The dynamics are complex, and typically chemical systems or biological systems have many state variables, just like the distillation column. This one's pretty simple. It only has 2 state variables, but it is an example of how, using neural nets and learning, we can learn to control another system that we really don't know a whole lot about, as long as we understand what the state variables and the inputs to the system are. A collection of training data for biological as well as chemical reactors can be expensive. You run it, and if you run it over a full range of inputs, you get a lot of crappy output that's totally useless and has to be thrown away. Also, the cost of failure can be high. You waste a lot of product, or things get really bad and the system explodes, like in the distillation column. So this system is a continuous flow stirred tank reactor. So what happens is that nutrients come in that feed into a tank here that contains water and cells, biological cells, so like yeast or bacteria. They eat the nutrient in the SF substrate that's coming in and is located in here, and then they produce a byproduct, some kind of other chemical that's a byproduct of their growth, or they themselves are the byproduct. And then flow is taken out of the bottom of this, and the flow rate is constant. It's W. So the flow in is W and the flow out is W. Level is maintained constant since the flow in equals the flow out. So what happens is a concentration of nutrients comes in. There's a concentration of cells in here and also a concentration of nutrients in here that are being eaten by the cells. What makes this additionally hard is that the cells adjust their growth rate based on temperature. It makes sense. But also the concentration of the nutrients makes sense if there's more food, and the concentration of cells. And this is where the nonlinear behavior comes in, because you would think you just keep putting more nutrient in and the cells grow faster. But that's not true, because if you get too many cells in there, then the growth rate goes down. And in fact, if the nutrient gets too high, the growth rate goes down, because there's too much nutrient and not enough cells. So in fact, the optimal operation of this reactor occurs in an unstable region. Okay, so here's the equations for this really simple bioreactor. Again, a real bioreactor would have hundreds of state variables and be more difficult to control. So, some definitions. State C1 is the cell mass. It's just a ratio of number of cells to the total mass of the nutrient or the substrate. So that's pretty straightforward. C2 is a measure of how much nutrient is coming in relative to what's already there. And so this is SF. It's the concentration of the substrate feed nutrient, and then S is the concentration inside the reactor. Again, W is the flow rate. So the equation model is in terms of these 2 state variables, and this is the input. So the equations are really conservation of mass, the rate of change of cell mass is equal to the rate of cells going out through the bottom and how fast the cells are growing. So this governs C1. So the change in C1 with respect to time depends upon how many cells are going out through the flow rate W. And then look at this. This is a nonlinear relationship in terms of C2, which is the nutrient level. And so the nutrient level is going to control how fast the growth happens, but it's nonlinear. So that's restated here. Nonlinear dependent on C2. And then, so that's how C1 changes with time. Makes sense. What comes in, what gets eaten is going to be the change. And then the rate of change of the nutrient, so this is C2, the nutrient ratio, is how much nutrients coming in, well that makes sense, minus the rate that it's being eaten up. So the nutrient level, change with respect to time, depends upon what's going out and then what's being eaten by the cells. So both of these are similar equations of what comes in and what's getting used. What goes in and how fast they grow depends upon how much nutrients there. Very nonlinear function of C1 and C2. So here's a block diagram. W is the input, C1, C2 are the outputs. I said this earlier, but the cells grow fastest at an intermediate level of C2, and then they grow slowly at very high or very low levels of concentration. So it's difficult to control because the optimal behavior occurs in an unstable region, and two different flow rates can lead to the same cell mass yield. So you could be on the high side or the low side and get the same growth rate. So here's a block diagram of their system. The paper, which by the way is posted to Blackboard, doesn't give a lot of details. I wish this paper gave more information about how they collected data and how they trained. But they show this architecture. Here's the reference outputs, and here's the current state of the system. So in a normal controller, you feed it current state and where you want to go. And then they have a neural net controller that figures out what input needs to go into the system to move C1 and C2 further closer toward the desired values here. This is a neural model reference adaptive control. Can he write the letters? So it's a neural model reference adaptive control architecture, which uses a model just like the track backer upper, where errors are calculated here and then back propagated back through the system. So error is back propagated through the model and then to this point to train the neural net controller. Their network had 2 hidden layers, 5 neurons each. And again, here's where the details are sketchy. They said they trained over a full range of data. And then they only show one result point. They say, well, we want a C1 of 0.113 and a C2 of 0.8902. And here's what they got. So the actual output as it settled down was 0.122 and 0.8778. They make a big deal of saying that it had to do with the fact that the model up here, before they did the backprop, wasn't trained as accurate as they would have liked. But I look at this and I say, well, this is not too bad. Right, we're comparing this number to this number and this number to this number. Now, I don't know what the normal operating range is, but they talk about how this is in an unstable region, so it looks like they're not doing too bad of a job of controlling. So this is another example of a neural net controller. Again, the architecture is neural model reference adaptive controller because they backprop the error through the model to train the controller. So this is like the truck backer upper. The paper shows a few more details than I've presented. It's on Blackboard. Make sure you pull it up and read it as well.